My dear students, in the previous lecture, we understood Bohr atomic model, postulates, limitation and scope, and we also understood de Broglie wave equation, which is applicable for dual nature of matter. That is, there we understood both radiation and matter possess both particle nature as well as wave nature. For that, we have derived the mathematical equations. So another important concept that is helpful to understand the structure of an atom is Heisenberg uncertainty principle. So according to this principle mainly going to predict the position of an electron around the nucleus, because we are clear that electron is revolving on the nucleus, and according to Bohr, electron revolving in a particular path, but the dual nature of light and other theory says that light does not have particular path. Instead of that, it has some region, some specific region in which the probability of finding the region is maximum. So this Heisenberg uncertainty principle concept, this principle mainly going to predict the position of electron around the nucleus. According to this Heisenberg uncertainty principle, it is impossible to determine position and momentum simultaneously and accurately. That means, at a time, either we can determine the position of an electron or its momentum, or that means velocity. Okay, so simultaneously you cannot identify both momentum and position. Suppose if you try to identify its position, you will end up with the error in the momentum. If you try to determine the momentum, you will end up with error in position. So that's why, there is an uncertainty. So that's why it is called as uncertainty principle. The mathematical equation for this principle is, delta x into delta p, is greater than h by 4 5. So here delta x indicates the error in position and delta p indicates error in momentum. So this is approximately equal to h by 4 5. So let us see the example for how this uncertainty occur. So dear students, let us consider a system in which electron is revolving on the nucleus. Suppose you are going to identify the position of the electron. In order to identify the position of electron, to locate the position, you are going to use some device like microscope. So through microscope, you are going to pass the light in order to see the position of electron. So you know that as soon as you pass the light has, it has pockets of energy called as photons. So when these energy particles, photon, are incident on the electron, these electron gain the energy. As a result, its velocity is changed as well as position also changed. That's why you cannot identify exact position as well as velocity of an electron. So this is the best example. Okay, and this expression applicable for all the objects. So because this is based on dual nature of matter, we consider both radiation and wave, radiation and light, as it possesses dual nature. So it is applicable for, even though it is applicable for all the particle, it is more significant only for microscopic particle. For example, let us consider in the previous example. So we understood that, suppose if you are attempt to identify the position as well as momentum of an electron using microscope, there you pass the light, because to see the object, to observe the particle, so you need the light. So if the light is incident on the electron, it gains energy, it undergo excitation, its position and velocity is changed. That's why there we fail to identify exact momentum or position of an electron. Okay, suppose, this is but if we calculate the uncertainty for microscopic and macroscopic particles, so for example, let us consider the two example which I mentioned here. Let us consider a particle of mass 1 gram. Okay, in this case Hy 45m. So here delta x into delta p is equal to Hy 45, because we know that delta p is nothing but mass into velocity. We are going to keep the velocity on RHS and we are going to send mass towards RHS and we are going to keep this on LHS. So this is the formula, delta x into delta v is equal to h by 4 pi m. Here if you apply the values to this equation, you know h is a Planck's constant of value 6.626 in 10 to the power of minus 34 and its mass 1 gram, that is 1 gram is nothing but 10 to the power of minus 3 kg. Then this is the value. This is the value you are going to get for a particle of mass 1 gram. Suppose, and this value is, see, you are going to get the value, so it is 10 to the power of 25 meter square per second. It's very small, very smallest value. So that's why we are going to neglect this. And so let us calculate the uncertainty for electron here. So you apply h by 4 phi m. Here mass of electron is 9.11 into 10 to the power of minus 31 kg here. And if you substitute the value, and finally you are going to get 10 to the power of minus 4. You just observe this value. So this is quite significant here. This value compared to the above value which I mentioned here, compared to the above value which I mentioned here, so this is very small, but this value, the value for electron is maximum. That is compared to the mass of, compared to the product of position and velocity value for 1 gram. So and this value is greater. That's why, so even we can apply this principle for all the objects, but it is insignificant for macroscopic particles. So for example, you apply the same situation to a ball, to a tennis ball. Okay, there you try to identify the position of an electron, through microscope. There you pass the light on it. So there the electron mass, the electron velocity get changed. But here if you apply the same experiment to the tennis ball, if you try to identify its position, the moving ball, so position as well as velocity, even if you apply the light do not affect anything on its velocity as well as its position. So that's why it is insignificant for a macroscopic particle, for example ball. Okay, so with these two examples we can understand significance of Heisenberg uncertainty principle. So dear students, finally we can conclude that this principle is very simple. Okay, the position as well as momentum or velocity of an object cannot be determined simultaneously and accurately. See the condition. So accurate and simultaneous measurement is impossible here. Okay, so we can measure accurately either position or velocity, not both at a time. That is the principles. So that we can understood by taking some examples. Okay, that is we attempt to identify the position of electron by using microscope, and we attempt to identify the position of dark ball, the position of ball in a dark room, and we apply the Heisenberg uncertainty principle to microscopic particles like electron and macroscopic particle of mass 1 gram. After calculating the uncertainty value, so we are going to get two different values. For macroscopic particle, we have got very less value, 10 to the power of minus 25 meter square per second, but for an electron we have got 10 to the power of minus 4 meter square per second. That's why the value is okay for electron. That's why it is, even though it is applicable for all the objects, it is more significant for microscopic particle than macroscopic particles.